Hi everyone, my tutorial is about the safety analysis environment of Aspen Plus software module. This module has some assumptions. First, I explain some definitions and the assumptions that is used in safety analysis environment, and the definitions of some context is explained in the next slide. There, I'll go to the simulation environment and solve a problem. First of all, I can explain about the assumptions that are used in safety analysis environment. API 520 and API 521 standards are used to calculate the pressure relevant device sizing equations. Also, the homogeneous equilibrium method is used in this module. The other assumption is that the design temperature and valve material checks are all full accordance for API 526. The calculations of low pressure storage tanks are according to this standard, and the calculation the thermal and liquid movement normal venting requirements are according to API 2000 code, and calculation of energy venting contingency are also done in this module. The evaluation of the requirement for normal and emergency venting for storage tanks are also performed in this module. Design calculations are performed under the scope of API 650 and API 620. Also, the pressure protection, overpressure, and vacuum pressure are done under the scope of API 2000. In this environment, the methods that are used are to quickly determine the orifice area and rated capacity of ruptured these devices, and also multiple valve configuration determination very quickly in this environment. And by using this module, the importing information can be done from Aspen Plus Safety Analysis environment to Aspen Flash System Analyzer. The other thing that I can explain about is that HEM, homogeneous equilibrium method. According to this method, the assumption is that the fluid mixture behaves as a pseudo single-phase fluid, and also in this method the density is the average of the two phases. Also in this method, the assumption is that the thermal and mechanical equilibrium exists as in two fluid phases through the PRV for high momentum discharge of the two-phase systems in nozzles longer than 4 inches or 10 centimeters. Both thermal and mechanical equilibrium can be assumed according to this method. And also in this method can be used for all two-phase discharge scenarios. That includes the supercritical fluids and condensing two-phase discharge scenarios. And also by using this method, Aspen Plus built-in properties calculator is used to evaluate the fluid properties by using the isentropic path. Some definitions here that are appeared in the safety analysis environment. The first one is the maximum allowable back pressure, which is the percentage of the set pressure that is allowed as back pressure for the valve. And this maximum allowable back pressure depends on the set pressure and the type of the valve. This maximum allowable back pressure is shown under the fluid properties tab. The other definition is the total back pressure, which is the pressure at the outlet of the relieving device. This total back pressure is sum of the buildup back pressure and the superimposed back pressure, that it can be constant or variable. The other definition is the superimposed back pressure. Is one of the section of the total back pressure and is the static pressure that exists at the outlet of the pressure safety device when it is required to operate. It is the result of pressure in the discharge system and it comes from the other sources and it can be constant or variable. The other definition is the build-up back pressure. It is the increase in pressure in the discharge header that develops as a result of flow after the pressure relief opens up. Relieving pressure is the other pressure at the inlet of the relieving device that is defined as the set pressure plus allowable overpressure. The relieving temperature is defined as the temperature of the relieving conditions at the inlet of the relieving device. Other definition is the allowable overpressure percentage. It is 21% of the set pressure for fire emergency scenario and 10% for all other scenarios. The other definition is the capacity relieving capacity, which is the flow rate of a fluid through a pressure relief device or a pressure relief system under the given set conditions and fluid properties. The other definition I can explain about it is the flow resistance L divided by D method. In this method, the determination of the calculated size of a pressure relief system is done, and in this method, the analyzing the total system resistance to flow is performed. According to this method, the flow resistance of the below items are done: the rupture disc device, piping components, entrance and exit losses, elbows, trees, reducers, and valves are taken into consideration in the flow resistance L divided by D method. Also, according to this method, when we use this method, the 8 and 5 rule does not apply, and when the rupture disc is installed in combination with the PSV, this method cannot be used. Another definition is the relieving flow method. According to this module, the wetted or API method and semi-dynamic flash method are the relieving flow method. Each of them has their own definition. The wetted or API method is the method for calculation relief load of a vessel that contains some liquid at relieving condition. That in this method, the latent heat of vaporization estimated to vaporize a specified portion of the hold of liquid in the vessel, and the sensible heat excluded, and all the calculations are done on a molar and mass basis. And the semi-dynamic flash method is the other method that the calculation of the relief load of a vessel that contains a multi-component liquid with a wide boiling point range. We can use one of these methods in the safety environment analysis. The other definition that I can do is the conventional pressure relief valve. Conventional pressure relief valve is a spring-loaded pressure relief valve whose operational characteristics are affected by changes in the back pressure, and the back pressure is the most important parameter in conventional pressure relief valve. The pilot operated pressure relief valve also is a pressure relief valve in which the major relieving device or main valve is combined with and controlled by a self-actuated auxiliary pressure relief valve that is called the pilot. And the other definition and context is the effective coefficient of discharge, that the value of for the ratio of the estimated relieving capacity to the theoretical relieving capacity for an ideal nozzle. Effective discharge area or effective orifice area is defined as a nominal cross-sectional area within the pressure relief device flow path that it limits the fluid flow through the pressure relief device. Rated capacity or rate of relieving capacity is defined the capacity of the pressure relief device that is determined by using the properties of the actual fluid that is flowed through the pressure relief device. When the certification test overpressure, also the overpressure is specified by the Code of Construction, and this is determination by using the effective coefficient of discharge and effective orifice area, or it can be determined by the certified coefficient of discharge or actual orifice area. Okay, I'll go to the simulation environment. First of all, I should run a simulation. The results are available. Before going to the safety analysis environment, it is required to run. It cannot be done. It cannot be go to the safety analysis environment before run the simulation. So it is required to run the simulation first. Results are available. I'll go to the safety analysis environment. As you see, in the safety analysis environment, a red ribbon box is surrounded the flow sheet. Okay, I'll go to Home tab, click on Add PSV. When I close the plus sign to the after the stream of the compressor that I want to add the PSV, blue square is appeared here. I right click on this, and this PSV is added here. Okay, I click on PSV and go to the required window. First tab is equipment. The unit operated that is protected is compressor. Operation temperature is according to the reference 54 degrees centigrade. The design temperature can be set manually or according to the reference. I drop down the list and select the reference. The design temperature is 54 degrees centigrade. That is equal to operating temperature. Also, I can choose the operating pressure according to the reference, and design pressure. Yes, the design pressure is according to the reference is equal to the operating pressure. It says create an emergency scenario, so I'll go to the other tab, that is scenario tab. I click on create scenario. I delete one of them. I double click on it, so I delete one of them. The first scenario is scene 1. The type of the scenario is selected here. For this scenario, I'll select the abnormal flow through the valve, and I click on sizing case. It says that the relieving temperature wasn't specified, and I should specify the relieving temperature. So I open the scenario. It takes some seconds. As you see, the type of the scenario is abnormal flow through the valve, and the reference stream is S12. If I choose the override, it means that other stream, the composition of the stream that flows through the PSV is different from the ES12. If I click on it, I can choose one of the streams that the composition of this stream is different from the fluid that is flowed through the PSV, but I don't want to choose it. Relieving temperature, I choose the reference. Okay, as you see the relieving pressure, I can edit the relieving pressure according to the standard API 521 or 20. Allowable pressure should be 10%. I can change it, but according to the standard it is a good allowable pressure percent, so I don't change it. Total back pressure, I can edit it. The total back pressure, atmospheric pressure is set here. Constant superimposed back pressure, so is equal to atmospheric pressure. Variable superimposed back pressure is set 0. Okay, I can change it to 1.5. Build up back pressure is 1.4, and okay, the sum of the variable superimposed back pressure and build up back pressure is total back pressure according to the definition. And maximum allowable back pressure also is 10%. Okay. The relieving phase method is a direct injection HEM. I have defined it before in the slides. It's an important thing. The required flow rates can be according to the reference. It is assigned according to the reference. Okay. It said it exceeds the 10% limit of total back pressure, so manually I select it. The orifice, I can select the orifice, for example M type, E type. It said exceeded 10% limit on the back pressure, so I should modify the back pressure here. It said the selected orifice is smaller than the calculated orifice, so it's a try and error until the yellow ribbon is going to green. I select G type, L type, no, R type, okay, it's green, but I examine the P type, okay, and the Q type is the last one, and I select this orifice area as Q. I go to PSV1, rate it. As you see, all of the things, the required flow, the phase, the scenario type, the size and scenario number all selected here and calculated here. I go to line sizing tab. The flow rate method is rated. It is the maximum flow rate that I used to this simulation. PSV flange size that is proposed is 6 inch, so the nominal diameter of the line sizing of the input should be selected. I use 6 inch, and the schedule for inline standard is selected, and the outlet 8 inch, and the standard, the schedule standard is selected. It said that inlet line pressure drop check error, maximum pressure drop exceeded, so I should change the inline and outline size. I select 8 inch and 10 inch. The maximum pressure not exceeded, okay, I select 10 inch and 10 inch for outline, and the inline pressure drop check goes to okay. Also, I can calculate the equivalent length. the constraint setting. The inlet pipe pressure drop limit is 3% of set pressure. Outlet pipe average velocity is 50% of the sonic velocity, and the outlet pipe exit velocity limit is 90% of sonic velocity. All of them are according to the standards. I don't change them. For example, I assume that one gate valve in inlet line and one gate valve in outlet line. As you see, the pipe length in inlet can be 20 meter or 30 meter. It is according to PNID, and the calculated equivalent length in inlet and outlet is calculated here. It's shown here. Okay, that's done. I can add another scenario here. For example, the scenario and the type of the scenario could be, for example, failure of a pneumatic control. I can change the sizing case from scenario 1 to scenario 2. If I change it, I should size the line sizing and the other parameters. I select this. It says the temperature should be specified. I open the scenario, failure of automatic controls. The relieving temperature is according to the reference, and relieving flow must be specified. I'll select the reference. It goes to green ribbon. Also, I create, if I select P-type, it says the selected orifice is smaller than the calculated orifice, so I should alter the selected orifice area, type Q. I'll be back to PSV1, scenario type, line sizing. According to this scenario, I select 10-inch for inlet and schedule, for example, 14, and 10-inch for outlet and schedule 14. It goes to green. I'll be back to rating. As you see, the selected scenario is 2, and the line sizing is according to the second scenario. If I'll be back to scenario tab and selecting sizing case. In rating tab, the scenario number 1 is the selected scenario to the calculations. Okay, I'll go back to the main flow sheet and add pressure rupture discs for S5 flow. As I close the plus line to S5 stream, the blue squares appear here. I right click on this and click on rupture disc. I select the reference from the drop down menu, design temperature also from the drop down menu, 5-bar gauge for operating pressure and design pressure 5-bar gauge, and 60.8 degrees centigrade for operating temperature. I go to scenario, create a scenario. For this scenario number 3, I'll click on this part and choose the fire and size casing. I click on it and open the scenario for fire. As you see, scenario number 2 and scenario type is fire, and the reference stream is 5. The relieving pressure is 6.05, and the total back pressure is 1.5, and the relieving phase is vapor according to the flow resistance method. For the required relieving flow, I use the calculation method vetted or API. Drainage or firefighting is present here. I also exclude the sensible heat, and the final vaporization according to mole basis is 10%, and initial vaporized is 10% according to base mole. Latent heat is calculated here, and I can select yes or no, but I select yes. Answer the number of vessels for rupture disc can be yes. The specified recommended dimension can be yes or no. If I choose the yes, I should select the diameter and the vessel tan to tan and liquid level of the vessel. But if I choose no, I should specify the exposed area 100 a meter to the power of 2. I also select the rupture disc diameter. For this scenario, I choose 30 centimeter. For rupture disc ID diameter, it says you should go to this line, sizing the line. So I should go to the RD line sizing, and I'll choose for this rupture disc size 30 centimeter, 12-inch nominal diameter of the line with schedule, for example, 80, and I select 12-inch for outline and 80 for schedule. It says it takes some seconds. Okay, it takes some seconds to run the simulation and finish it. We should be patient in simulation. There's no problem here. Sometimes it takes some minutes to simulate. Okay, the ribbon goes to green. As you see, the line size results calculated DP for inline is 0.9 bar gauge, and for outline the calculated DP is 2.3 for rupture disc, and the other ratings and the other information is here. The required flow, total orifice required, and the total selected orifice is shown here, and that's done. Thank you for watching. Goodbye until the other day.